Thank you for inviting me. And so the ones of you that know this rock band U2, there's this introduction that Bono does to a song that is, this song is not a rebel song, this song is Sunday Bloody Sunday. And the introduction is to cut to the chase, right? Because there was a lot of controversy. And so my message here is also to cut to the chase. So most security vulnerabilities are software bugs. And although I don't see this sufficiently said, I think it's, for me at least, pretty clear. And I hope I'll pass the message and you tell me if it is convincing or not what you believe about this. So this lab, you might look at it, you might see the name and say, okay, this looks like LICS, right? Laboratory in Computer Science. The "in" sounds a bit weird there in English, but it's intentional to sound like LICS, and LICS is a very important conference for us all, right? Logic in Computer Science. And what I use are basically logically explained algorithms and language-based. So this is not, I hope no one gets offended by this observation. It's just to tell you that I'm not going to show technicalities. This is not a technical talk. This is a talk about why I believe security vulnerabilities are bugs. But everything that I'll mention is, in the end, translatable to algorithms, reasoning about code, right? And my background is concurrency theory, but this means that although a big part of what I'll show applies to sequential programs, the tools and the way of reasoning is based in concurrency theory, and I'll get back to this later. Okay, so I wanted to start to show you a major flaw, so a major problem that happened 6 months ago that affected millions of people. And the irony, it was a software security update. So there was this very much used software to ensure security for web-based services, CrowdStrike. And they made an update that was not memory safe, basically. And Windows machines that received this update crashed badly. So badly, you got a blue screen of death, right? The infamous BSOD that for a very long time we did not see anymore in Windows, right? So Microsoft was getting proud and saying that this doesn't happen anymore, right? And it just happened in 8.5 million devices in the world on July 24, right? And because they got a memory buffer overflow. It didn't happen in Linux systems or iOS. We can discuss offline why was this the case, but it was pretty severe, the problem, right? And it affected really thousands of entities around the world, and it costs a staggering amount of money. Okay, so I don't want to give you examples and keep on talking about software bugs and their effects. What I would like to call our attention here is that I see there are mainly, when we're talking about bugs that are not connected with the correction of programs, that are connected with causing these kind of malfunctions that make things go really wrong, they are basically connected with either data errors or data representation errors and incompatibilities between these representation errors or the data we want to store in a particular space that might not have enough space to store it. Data consistencies, so concurrent updates that are not consistent, and the machine starts having divergent views of the database values, and at some point just decides to stop. Not respecting data usage protocols. So these distributed attack on blockchain, these autonomous organizations that had this attack, they did not foresee that you could make a bank transfer to yourself. And so it was, I call it a protocol error in the sense that there are roles. There's the sender and the receiver, right? The person that is giving money and the entity that is collecting money, and it's for us somehow, if you think about access control, completely basic that you should distinguish these. If you're raising money for some purpose, you distinguish whoever's people sending and people receiving. The sender and the receiver should not be should not have the same role, should not be the same person. It was as simple as that, this kind of attack, right? That caused this. Then you have many issues regarding memory safety, and these issues, they crash machines, but they also expose information. You can have memory leaks, exposing information that is not supposed to be public or not supposed to exit some parts of the machine. And so I'm concentrating on, when I talk about software bugs, on these 4 kinds of situations, right? Not on other kinds of situations like the also infamous post office software that was saying people with local post offices in the UK and were accused of taking money from the company. Many went to prison, and this was also an accounting error, a correctness accounting error in the software, right? So I'm not talking about that kind of bugs, although they are really very important. Okay, so I'm sorry. There is this statistics that I'll give you more details afterwards, that the cybersecurity attacks, 1/3 of them are exploits on vulnerabilities on the software. And these vulnerabilities, the software vulnerabilities are so important that there is a catalog of them, right? And this catalog of them is also classified according to the weaknesses that are exploitable. And this is public these days. And this catalog is called the Common Vulnerabilities and Exposures. And these are numbers from the end of 2024. So I went last week to the website. Everything is public. So in 2024, we had 40,000 vulnerabilities reported. The database has 176,000 vulnerabilities there reported. And these 40,000 in 2024 are a 39% increase from 2023. And this annual increase is always like this, 40, 50% every year of increase of vulnerabilities being reported. And you can see here in this graphic that the largest number go from serious to critical. This red is really very, very serious, critical vulnerabilities that can be exploited to take control of machines. And there's a large number, almost 20,000 right, here. And this is the global names in the 176,000 that are in the repo, right? The top ones, the top vulnerabilities being exploited are cross-site scripting, so calling using code services in other sites, memory corruptions, and code injection. These are the top ones that you can find here in the repository. And we should do better, right? For a long time we know that the solution is not a posteriori. It's very difficult to attack afterwards. Many of these exploits are what is known as the zero-day exploits. So they don't, when they are public, they were already solved, right? But many are just, they become public they already solved, but we don't know if they were exploited, up until what point they were really exploited. And the point is, we have ways of doing better software and to avoid these situations. So, code injection, memory corruption, this is known for a long time, and we have not only techniques, but in programming languages, we have disciplines and ways of avoiding this to happen. And also, we have also tools to inspect software and find these kind of situations. So it's puzzling at the same time, the numbers. So my first message here is that there is, for me, clearly a mismatch between what we experts of the discipline know and what is the practice of the industry and what is the expectations of the regulation and government bodies. Right? This situation is only possible because although the society is already alerted, there is not enough pressure to avoid this to happen. We have the science, we have enough science and technology to avoid it to happen, but it still goes on and on. And this is only because it's possible to do it, it's allowed. In the end of the day, it doesn't cost much to have these bugs most of the time. Right? Most of the time, it's economically viable, it's economically feasible. It's better to have the bugs than to avoid them. Okay, so, I'm sorry. Things are starting to get better, and so I'm putting here some official documentation from 2024. This is in the communications of the ACM. Many colleagues of ours, so at least some of you may recognize Peter Sewell, Jessica Clark, etc. Some colleagues of ours published this letter, I would say, that it's time to, well, let's standardize principles and practices to memory safety, right? And this is an interesting article, not technical at all. It's just calling ACM to put pressure on regulatory board and to ensure that we find ways of building software with better practices to ensure memory safety. And this, yes? This is 2025. This is the last issue of communications of the ACM. I believe it's, well, I got it last week. It's January 22, 2025. So it's the last issue of the communications of the ACM. And this is March. Actually, this is February, but it's a press release. The document was public in March 2024. So the White House, this is the Organization for the National Cybersecurity of the White House, and they say future software should be memory safe. There is a document, so this is the press release presenting this report, this document, and the document, puzzling enough, says at a certain point, don't use C, use Rust. An official report of this body of the White House, right? And then you have, a few months later, the foundation that governs C++ saying we're going to memory safety as well, right? You have this report of this foundation for C++ saying we are able of being memory safety. You don't need to move to Rust. We'll be there. Okay, and so, I'm sorry. This is also quite recent because this is January 16 this year, an executive order about cybersecurity. And this executive order is imposing security standards for companies. And these security standards say that they should demonstrate the security of their development process. And I believe this is science fiction, because this is something I will come back at the end of the talk, if I am able of respecting the time, that although we do have the tools and the science to ensure safety, to be able of saying something that software companies should demonstrate the security of their development process is really, really strong. I don't think software companies will be able of doing that these days. But this is an opportunity, a challenge to us, right? And I'll try to be back to this at the end. Okay, so in the European Union, we have the Cyber Resilience Act, and this says it's basically aligned. Cybersecurity standards for products. These products should contain a digital passport, with components. And it's saying that it should ensure cybersecurity throughout the life of the products. So it's also asking for a resilience that I don't know if we have means to actually ensure. And moreover, you also have this is I think from last year like February, and this is like May, and this Data Act will be a law, an official law in September this year. And the Data Act asks for two things: interoperability between IoT devices, and, puzzling enough, it lays out requirements for vendors, and by some reason I don't know, of smart contracts, so it's not software, it's just for smart contracts, to correctly carry out the provisions of data sharing agreement. So they are asking for correctness with respect to the data sharing agreement, but only for smart contracts. Not really every software that runs in the IoT devices, right? But what I want to show here is that from last year, there is a fundamental change, right? Something stirred up this fundamental change in the government, in the bodies and regulations and governments, right? And there is this situation where they are ahead of us, because you have politicians asking for things that don't exist, really. I don't know if they are aware of that or not, but we have this puzzling situation. For many times, there was nothing. We had technology that could be used, and it was not used because it was too expensive, no need to use it, and suddenly there's these 2 steps forward, and they are ahead. And this is unimplementable, I find it, at least. Okay, so this was just the motivation and telling you what's going on. And now I'll try to make a general scenario. How do we diagnose these problems? How do we treat them in concrete software? And then dive a bit into my approach and my suggestion. Lightweight automatic methods like static type systems might be a help to the programmers. That's my idea here. Okay, so we have laws to build resilient software. Things will continue to happen like this, right? Because the situations are too complex. We deal with such a complex situation because we have the software, the compiler, the hardware. The compiler is not a single entity, right? You have the compiler from the high-level language to the intermediate, from the intermediate to the low level to the metal. So and the number of interactions that happen in all these parts are so many that it's really difficult to avoid that these kind of situations happen, right? So, and we all have this experience, right, of solving problems to create yet more problems. The CrowdStrike was an update, right? They were doing an update to their own software. Right? And so the typical idea in most software companies that I know is this one: test, 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 debug, debug, debug. But this is hopeless. We know that, right? It's good to find problems, not to show the absence of problems. So to be able of approaching gradually this idea of ensuring correctness, of being resilient, we need better than just test, right? And this, of course, we know for a very long time that is difficult, but we should strive for it, right? I also like a lot this manifesto, the Verified Software Initiative of Tony Hoare, Gary Levins, Jayad Mishra, Shankar, etc., where they say we envision a world where programs are the most reliable part. It may fail in other places, but at least the code, the initial code, is the most reliable part. Should be verified and correct, right? And the opening, this is the first sentence of this document, of the manifesto. And it's a long-term research program. What I'm saying here is that we have, for actually a long time, we were feeling like fighting against windmills, right? Because it was not economically viable, it was not necessary, so we were trying to sell something no one wanted to buy. But these days again, probably we have an opportunity, right? And also, big players start showing interest in these, like the Kata OS. This Kata OS was actually to build machine learning platforms. It was used by Google in their machine learning platforms. And the kernel, one of the kernel of Linux, Cell 4, right, that it was, the code was written in Rust to have memory assurances, and correctness was formally proved, right? I think it was Isabel they used, if I'm not wrong. Anyway, we know for a very long time how to approach the problem, right? This is a 1949 paper, and checking a large routine. And basically it was doing inductive reasoning on this program, on this routine. It was doing inductive reasoning to prove it's safe, right? There was a first order logic statement about the correctness of it, and it was the reasoning, although informally, is to prove mathematically soundness and completeness of the code that is doing some elaborate calculation with respect to the first order logic formula that explains what the routine is supposed to do. So very early in beginning. Well, we all know what are the alternatives, or what are the recipes to attack this correctness challenge. You can use deductive methods, right? You build a logic to reason about the program, and you make a proof, like in a logical proof system. You make a proof that the code adheres to the specification. Automation here is not very high, typically. Well, you can be dynamic in the sense that we run not exactly the software, but an ideal version of the software, a model of how the code works, and try to show properties of the code. Here you have typically, depends on the person doing the proof, what are the properties? We choose the properties. And this is a difficulty that if we have time, or in the break after, we can discuss, is how can you be complete in the sense that we thought about all properties? How can one be sure the software is safe in the sense that we anticipated the right properties? And I think both of these approaches have this challenge, right? In deductive verification, you have the statement you want to prove, and you do manually, or sometimes more or less automatically, the proof. In model checking, the proof is automatic on the model, but we still need to think about the properties. We fix a few properties, like we have a railway system, no two trains will cross in some crossing junction at the same time. It's impossible that two trains will be allowed to pass this cross at the same time. But we need to think about these properties, and we are always thinking about, were we complete from a safety point of view? And I don't think this is solvable, right? A third approach is the static analysis, typically with type systems. So these two, they have the decidability issue, right? Because we can not prove properties that are not decidable. With type systems, we do a miracle, because we prove undecidable properties over approximating or under approximating. So we just forget about being precise and give some answer. And either we are worried that something never goes wrong and we over approximate, or we are worried that what we say is true and we under approximate. Right? But type system, in these proof systems, since they are a logic, they prove any property. Type systems are proof systems tailored for one property, typically. And the property is fixed. It's not chosen by the programmer or the user of the type system. Whoever developed it decided this is the property, it's only for this property, but the code will, if the compiler accepts it, the code respects that property. If we are over approximating, if we are under approximating, means when the compiler says no, it is right, the problem exists. There are no false positives when we under approximate. Okay, so since I did not know what the audience was saying, there are many tools this day for deductive program verification. I'm using the wrong logo, sorry. And well, very simple, very simple examples, mainly for students, about how to specify and prove these. And here the proof is showing that the program, the code, fact of n, gives the same result of the mathematical definition of the specification of the factorial function, in this case, n bang, that is primitive in the system, right? Okay. Many different approaches to this kind of way of proving things, right? Can be for functional language, can be also for imperative languages, so Daphne, Key works with a version of Java, so with the sub-language of Java. It requires one to write annotations in this Java modeling language, JML, right? Daphne works with its own language. And this, I believe, is one of the barriers to use this approach, is that most tools have their own language, and not the language that programmers use. Right? And most tools these days extract, if we are managed to do the proof, then we get certified code in a mainstream language, or Camel, C, etc. But this is not the code the programmers wrote, and it does not deal with legacy systems. So it does not deal with code already existing. It produces new code, certified, but does not deal with the reality that exists already, and it's governing our machines everywhere. Okay. Doing these proofs is quite demanding, both in expertise, training, and time, of course. And scaling it is even more demanding. I find natural that specifying what we want as a property is a lot more code in the end than the program itself. But this is also scares the industry people. Because they say, what, I spend don't know how many time to produce this million of lines of codes in this project. You asking me to produce 2 million lines of codes in 10 times more time to issue something? No way, I'm not going to do that because no one forces me, right? And that's, I believe, one of the main reasons, right? The cost to develop this kind of proofs. Okay, so model checking. We have a set of properties in some language, but we need to abstract away from the real code. We need to represent the system we are implementing in some, well, to be able of really reasoning finite state model. And even if it is a finite state model, it can be huge. And we have the so-called state explosion problem of being able of putting the machine algorithmically finding if the property holds or not, when the number of states is absolutely huge and the number of possible paths linking these states is even bigger, exponentially bigger, right? So we have this difficulty. Moreover, it depends on the expressiveness of the logic, what we want to say. And we are actually encoding our intuitions and encoding natural language requirements in logical statements. And this is a part that I believe we are really far from really understanding how to do better, right? The requirements in natural language, the requirements that we understand intuitively, how to translate them automatically to logical formulas, right? I believe we are still quite far from getting this. And since we are far from getting that, we are always going to have problems because we simply did not think about a particular formula or wrote a formula that is not exactly what it should be. And it was proved correct with respect to that spec, but not with respect to the situation anticipated, right? So, moreover, computability tells us anything interesting is undecidable. Any property that is really a bit challenging, any property that is what we want, is undecidable. So, not easy here to address this. Okay, so model checking has been used a lot. I don't want to say it's not a good approach. It has been used actually a lot. There was Intel started using it heavily after this bug in 1996 or 97. Well, in the middle of the 90s, they had this bug where there was the division algorithm was not correct. But it was only appearing with very big numbers, really big numbers. And there was this data scientist colleague that wrote to Intel saying, I'm getting these weird results that I know they are wrong. What's going on? Intel said, well, you are wrong, not our Pentium. A few months later said, okay, you might be right, but this never happens. And a few months later, they paid millions and had to replace the processor, right? But it took a long time to really acknowledge the problem, and it cost a lot, and they started using it heavily. And so it's clear when a company has to pay too much, it decides, well, let's avoid the next problem and start using methods better than just testing and debugging, right, to solve the problems. Okay. There are many tools to do this kind of approach. For concurrent discrete systems, MuCRL is very used. For everything that needs a probabilistic reasonings, we can use Prism. Spin is also used for protocols. Real-time systems, UPAL. So this is just to say that there are many offers, many different complementary tools around to deal with these. And Again, one difficulty with these tools, all of them, they have their own language. Some can can translate some higher level code or produce higher level code, mainstream code, but they have their own language. So we have a translation problem. Something is necessarily lost in translation. Right? There are tools addressing directly higher level languages. A model checker for Java bytecode, not really Java, but for the bytecode. So it depends on the translation of Java to the bytecode to be correct. Right? But there are already model checkers for mainstream languages. They all have this approach of reasoning about a model, not really the code itself. The algorithms don't analyze source code. They translate source code in something that represents the system, finite state, and do the analysis on that. Okay. Then we need to reason about these translations. Are they sound? And then we have also the problems of decidability. And then we have the problems of state explosion. All these are barriers also in getting the right results in these days. Okay, is it scalable for real software? Right. Okay, so summing up, general infantry coders, so those footstep soldiers, don't deal with this kind of stuff, right? They don't even deal with preconditions in the code. These days, most languages allows you to put requires. One thing I get systematically in third year and fifth year students, they don't like to write this kind of things. They really resist writing these logical specifications. So deductive approaches are quite demanding. They need exceptional programmers. Dynamic, fine, but they are neither sound nor complete, difficult to scale. They reason about models. It is used a lot with very good results, namely in hardware and in specific software, for instance, for railway systems or avionics systems, but not general enough to deal with languages for websites, and 90% of software vulnerabilities of security attacks are on websites. And these are developed in other languages, not really. They are not really these niche situations. So, static is what I'm proposing you. Okay, static software verification exists a lot. I'm showing you here two of the main tools that are more successful and used in mainstream languages, Clouseau and Infer. One using abstract interpretation, the other using separation logic. They deal with code. They deal with millions of lines of code. Right? They had this motto when they were developing this, go huge or go home. They were using this known motto to develop Infer, to be able of dealing with real code. The problem of this static approach is false positives. Many times the computer says no, but the problem doesn't really exist. So they check automatically these problems that crash programs, null pointers, overruns, so overflows, underflows, divisions by zero, precisions. They take care of that automatically. But they are a bit annoying, right? First, they are supposed to be used by the GI coder, but the GI coder needs to understand the messages, and the messages sometimes are quite technical. Did any of you use Rust already? No, okay. What do you think about the compiler error messages in Rust? I've seen this blog a few years ago of a guy saying, why is the Rust compiler teaching me computer science courses every time? I think. it's just so messages are sometimes very elaborate, difficult to really understand, and moreover, tell you the problem, not the way of fixing it. Just tell you, okay, no, this is not good. And sometimes the programmer looks at it, inspects the problems, inspects the message and says, there is no problem. The tool over-approximated. It's saying it's not correct, it's not safe, but there is no problem actually. And so it forces defensive programming. And this is also costs money, defensive programming. It's not only annoying, but it also costs money. Defensive programming is putting if then else's everywhere. Like if this parameter is different from null, then, and sometimes programmers say, but I wrote the main function. I never call this function, this client function, with a null value. My main function does not do that. But he needs to write the if-then-else condition to a defensive programming to infer his code is correct. Right? And this happens a lot. And there are approaches these days to avoid this using the so-called incorrectness logic. So it's a dual of OR logic that instead of over-approximating, under-approximates and says every time we find the problem, it exists. And develops the theory for that. But it's not complete. So there might be problems that are not found. The only thing that they are guaranteeing is if a problem is reported, it is real. But there's no way of being precise. Either we over-approximate or we under-approximate. Rice's theorem does not allow us to be precise. Gödel incompleteness theorem does not allow us to be precise. So we need to approximate with static approaches. Okay, so these tools are all quite demanding. What I'm going to tell you about is a bit of the work I've been doing. It's about type systems. So I was talking about Maseratis and Porsches, Cluso, Infer, and now I'm trying to sell you a Fiat Uno, right? But the point is that we can get some of these properties in a lighter way. And that's the approach I'm going to show you. It's a bit more technical now, but we can get it in a lighter way. And avoid that the bugs appear, because the Cluso and Infer and all these tools are post-mortem. You analyze things that went wrong. A type system is a mechanism of assisting the programmer to build correct software. Right? It's at the same time the code is written. And I think this is a big advantage. That you're not writing code and then analyzing it and getting problems and fixing and debugging. No, you write the code, and as you write the code, you have this tool always running with the code that tells you if you're doing correct things. At the same time you are developing. I think this is one of the big advantages, just following the extra moto. Don't put bugs there. The problem of debugging is that you introduce the bug. So don't put the bugs there as you develop the code. Okay, so the case for static type systems. Right. Okay, so if we choose to have one property to prove, and we get type safety, meaning our code respects that property, these algorithms work fine. Right? And the recipe is this. Instead of having a general approach, deductive or dynamic, where you can prove every possible property that your logic allows to write, and that the system is able of reasoning with, let's concentrate on some very concrete properties and develop a reasoning system, a proof system, only for that property. But this proof system is a lot more efficient because it's not equipped to allow for reasoning in all the logic, is tailored to this concrete property. And this is the advantage that makes things lighter and allows to then assist the programmer as the code is written. This is the approach. Rust is a very successful language in this respect. It ensures memory safety and thread safety by the type system. The type system ensures it. And if you install a Rust analyzer in your favorite editor, you'll get these red circles in the right line telling you there is a problem here and explaining, giving you a computer science course why there is a problem there, right? There are limitations. The typical problem with Rust is that it does not allow many things we would like to write. You cannot write a double linked list. It's not safe in Rust. So if you just use safe Rust, you cannot write a double linked list because Rust does not allow aliasing. Rust has this discipline called AXM, aliasing short mutation. You can alias anything if you just read. If you're going to write, there's no aliasing allowed. And this is, although Rust, the terminology is AXM, this is known from the beginning of the 90s when Philip Wadler was saying linear types will save the world. He has this famous paper with this title, Linear Types Will Save the World. And the linearity is this: each time you need to mutate a reference, it must be linearly owned. Only one component of the program has right access to that. Rust takes it one step further. When you want to write something, no one can even read. And this is needed to ensure thread safety. This is needed to ensure consistency. Because if you read something that is going to be mutated, you might be taking decisions with the wrong information. And that's why the Rust type system does not allow even to read a reference that is going to be mutated, right? But it's not easy. So what is the motto? And this starts getting inspirations from concurrency theory. The motto is, well-typed programs do not go wrong. This is the abstract of this paper in 1978. And in the abstract, curiously enough, because the paper is about an extension of lambda calculus, right? It says the aim of this work is largely a practical one, in the sense that it's about writing a type system. It's about understanding what it means, type safety, to prove this property that well-typed programs do not go wrong. And this motto hides two technicalities that are quite demanding. The safety property is on wrong. We need to define wrong. And the other thing is we need to define a logical system to decide that the program is well-typed. You define the program is well-typed. This logical system does all the reasoning in order to assure that wrong never happens. And in the end, wrong is a value of the language. You need to encode wrong as a value of the language to make sure that the type system does not allow programs to run into it. It's a very interesting paper and a very interesting research program, ensuring that well-typed programs do not go wrong. And this is not true in most languages that we use these days. Right? Python is not type safe. Java is not type safe. And the main problem with Java, with type safety in Java, is null. Null is a value of every type. Java with generics breaks easily because of this. You write programs that are well-typed and run into null pointer exceptions. Okay. Cabell Rust claimed to be well-typed. When I say claim, is that there is no formal proof The languages are too big for the effort. It was not possible to make this real proof for the whole language, but we have evidence for for parts of the languages, for sub-languages of it. Okay, so the problems, as I was saying, so in the first slides when I was showing the bugs, I said there are problems related to data, but there are problems related to memory. And there are problems related also to the flow of information in a program. So data is not the only source. Flow is very important, memory is very important. And what I believe fits this research program of going in the direction of ensuring the absence of security vulnerabilities in software is to concentrate on avoiding crashes. Right. Avoiding crashes would be already a big step forward. Right. Okay, so what are the typical situations? I'm sorry. This is already well understood. Type systems deal with these. Rust deals with this kind of situation. Null dereferencing, dangling pointers, right? But most languages don't really control this situation. Not even C++ these days controls these situations. So I believe in an object-oriented language, we get these kind of problems many times by calling methods at the wrong moment, or with the wrong kinds of arguments, or in the wrong order. For example, the iterators. How do we deal with iterators? We don't call next before has next. If you start calling next in a loop, you'll run in a null pointer exception for sure. And the discipline is first call has next, then if has next returns true, call next, right? This is exactly the same behavior that dealing with a file should have. First call open, then call read, right? So the situation in most programming languages is that not only we have insufficient data safety because reference memory is data, but you also have no flow safety in these kind of situations. But we can put them together. So if you think about the file, this is a picture, a graph, showing what is the discipline to use a file. And this is, I'll call it a protocol, a usage, an object usage protocol. You should use files like this. And now, my concurrency theory background tells me that you can look at this as a transition system, a labeled transition system, right? So this is a state, the state where the object representing the file is closed. In this state, the transitions that you can do is calling the open operation. When it is open, you go into a different state. The object is, the reference is in a different state. And here you have three operations that you can call. And these operations make transitions between states. And we have a lot of theory to reason and to make sure these kind of things are correct. Why don't we put them together? The data safety, the memory safety, and the protocol safety using these kind of approaches and using linearity. These are the so-called behavioral type systems and for mainstream languages. Okay, it starts with these observations. Stateful objects have a protocol. Not all method is callable at all times, if the object is stateful. Right? If we want to respect it, we need to be careful. And so let's use these behavioral types, these entities from concurrency theory that allow us to connect state and operations and allow us to reason about that, right? And we will get this guarantee that if you respect the protocol, the type system will ensure the program does not go wrong. And wrong will be a crash here. Wrong is running into null. Right? We call it type states because it's a representation of states that is done with a static entity that is a type. Okay? And these type states declare valid method usage sequences. If you just do these, things will go correctly. And we have to associate one of a type state with each class, with each constructor of objects. So let me show you an example of a type state, a textual description of the type state to deal a line reader of a file. And this is the graphical description of the type state. Maybe you want to look here. We start in this state. The only thing you can do, the code in the main function, the only thing it's allowed to do, otherwise the type system rejects, is to call the open method. It must call the open method with some argument of string type. And you might see here that, for instance, code injection would not respect this kind of type annotations. So a basic way of avoiding code injection is a type approach. Of course, you do not type the code of the attacker, but you can build a monitor. You can put this as a machine controlling the requests of clients and only allowing requests that follow the protocol, the order and the right types for the arguments. Okay, and this translation is done automatically between this textual representation and the automaton. We have a small tool to do this automatically, to go back and forth. And now this textual version is what we attach to code. So here is the type state, the textual version, that is here. So we have this. There is a file called line reader protocol that contains this text. And this file is read by the type system to make sure that this Java code respects the type state. And crucially, that the main function will generate possible runs that always follow this. That's the idea. Okay, so we need to associate these descriptions with the behavior. We are asking for a bit of work from the programmer. So the GI coder needs to draw this. But I believe this is the minimal thing to ask. I don't see how a programmer writes Java code without thinking about this. I believe to write this code, you are actually thinking about this. And I'm confirming this with first-year students when I teach Java. And these drawings they do before writing the code, and they are natural. Okay, and now, well, you declare it, and at compile time, we check. There's a caveat. To avoid interference, we control linearly the access to objects. And this is a big limitation. We are basically in the same situation of Rust. To use an object, we impose a linear discipline. And this is a severe limitation. I'll get back to it in the last slide. And there are many approaches. Some of the approaches here. A small language, the minimal object-oriented language, or tools for Java, a particular language called Plaid in CMU, session type Java, SJ. So there are several different tools for this. And what is the idea? So what is the recipe? Let's follow an Occam razor approach. Right? First, a sublanguage. We take a sublanguage and we define precisely for this sublanguage the syntax, and for each component or for each for each primitive, how it affects the abstraction of the program that is the type state, right? With type systems. We define an operational semantics, and the operational semantics should define wrong. Should precisely with rules tell us when does a program reduce to wrong. And the type system prevents wrong. And a type system is a decidable algorithm. Over approximates, but it's a decidable algorithm and it's automatic. You're writing code and the type system is working in the back. You get the red circles in the right line saying there is a potential problem here. If there are no red circles, you ask the compiler to compile the code, you may get errors, or if the compiler accepts your code, well, type programs will not go wrong. You will never see wrong in your programs. And wrong is a precise value in this language. So we started this approach in a functional language a few years ago. This is a 2006 paper in theoretical computer science. We said, okay, it should be easy to move from a functional language to an object-oriented language. Easy meant 4 years. Just for you to understand, maybe it's us, me in particular, that I'm not clever enough to make things go faster. But this easy step meant 4 years. We built this tool, contribute to this tool called Mango that I told you. And Mango addresses mainly, this is wrong. This is the wrong that we avoid. Improper enforcement of behavioral workflow. And this is a classification. This is the common weaknesses enumeration that is classifying the CVEs, the common vulnerabilities exposures, right? And Mango mainly addresses this with a very precise, rigorous value for wrong, but to translate to security people, this is what we address in Mango. Okay, in particular, it does not address memory safety. Okay, so in 2010, we had this approach that the theory on Mango. Mango is from 2015. In 2020, we reached a point where we could deal with memory safety. This span of time means that 3-4 people teaching full-time at the same time, average people, I would say, take this time. This is the time span that needs to get this kind of results, right? And so it also says that we need a lot more, an effort a lot bigger to make things advance faster, right? So we had this paper on behavioral types for memory safety, right? And then we built, with the help of a student, a checker for Java that moved from Mango, that was only protocol compliance, to memory safety as well, including memory safety as a byproduct of protocol compliance. And this is the GitHub README, part of the GitHub README showing it. Oh, sorry. And now we are addressing this other CW, memory safety, right? And, well, if you're writing object-oriented code, you need subtyping and casting. And so 2024, we have finally a paper explaining how to incorporate subtyping and casting here. And this is a benchmark we wrote with simple examples. But the idea of these simple examples was to be paradigmatic. So some code controlling robots, controlling drones, cars, the typical iterator. Java accepts all this code. We wrote code that Java accepts, compiles. Some of these cases, the version 2, always version 2, or in this case version 3, goes into problems. Our extension, dealing with subtyping and casts, rejects everything that goes into problems. The type system does not allow wrong in these cases. Okay? And this is just an example to explain you what do we mean by subtyping. So we have here the class car, where there's only 2 states. The class SUV now has 3 states. The transitions are basically the same, apart from switching, and you need to reason about subtyping. You need to reason when you can go from car to SUV, so downcasting, when you need to go from SUV to car, so upcasting, and the theory is described there. It requires a bit more of annotations to say that if you have a parameter of type car, then the state it should be is on. Otherwise, you cannot call this method. Just a bit of examples. Okay, to wrap up, buggy software, it's life. It was the answer of the industry during many, many, many years. It is now clear that it's no longer the case. First, a lot of people and relevant people crying, these are just bugs. Take attention to them, they are just bugs, right? And sometimes they are hardware bugs. Sometimes and these hardware bugs are being addressed with kernel functions disallowing some kinds of behaviors. And Linus Torvald actually was saying this not to justify not accepting a pull request to the Linux kernel to avoid a hardware bug. And he said, enough is enough. I'm not going to accept this pull request because this is just a bug. Get your software, get your hardware correct, and don't mess with the Linux kernel. And laws and regulations are taking scope. So, the challenge now is this automatic safety. Get programs right, not only in the sense that they don't go wrong, but also in the functional sense. And to get it in the functional sense, we need types that encompass properties, the so-called refinement types. We need this, and maybe we can move forward to the science fiction scenario where software is correct. Thank you.